braving the rain and the cold weather. How are you guys doing? Feeling all right? So this is week 5 of the class, and this is almost halfway. Stanford has 10 weeks of teaching any quarter, so this is halfway, and this is kind of reaching the midpoint in the class. So this is the last class I have on traditional applications of nanomanufacturing, that is making logic, memory, DRAM. And today I'll try to build up on the knowledge that we have built up over the last 4 weeks. We have talked about FinFETs, we have spent a week talking about NAND flash, we spent a few videos and in the homework problem talking about DRAM. So this lecture would be talking about the recent advances in that area. But if you have any questions, or if you have missed a class, or if you don't understand anything, just please feel free to interrupt and ask questions. And so what I want to cover today is essentially a bunch of things which have happened in the process technology space, and these are very important things, but these are largely uncorrelated topics. So these are very important things: high aspect ratio structures, ALD, air gap technology, strain engineering. So what I was struggling over this last weekend was how to arrange them into a theme so that it becomes coherent and we bring some commonality to it. So what I've tried to do is organize it under 4 themes, and but we'll be covering that topic that I discussed, that I just mentioned on the last slide. So the first common theme that you see in process technology is this issue of deep trenches and skyscrapers. So I want to relate it to the deepest trench and the tallest skyscraper, and we'll relate what we see in current day chips. How does it relate to these deep trenches and that skyscraper, right? So let's look at the deepest trench in the world. It's Mariana Trench. It's located off the coast of Japan, and it's 2,550 kilometers deep. So it's around 1,500 miles deep, and its width kind of varies from the top to the bottom, but on an average it has a width of 70 kilometers. So aspect ratio, which is essentially just my my depth or my height divided by my width, for this Mariana Trench, which is the deepest trench on the planet, is this 2,550 divided by 70, or the aspect ratio of 37. And it's so deep that there have been only 2 manned expeditions to the bottom of the trench. More recently, you might have heard David Cameron, the director. He recently went in there and was at the bottom of the trench. So keep this number in mind. That is this aspect ratio of 37, right? So the other thing is, let's look at, we looked at deep things, let's look at tall things, right? So the tallest skyscraper in the world is this Burj Khalifa Tower in Dubai, right? So this has a height of 828 meters. Its width kind of varies. It has that Y-shaped design, so its width at the bottom is 175. Its width at the middle is 100 meters. So aspect ratio of this would be, the height divided by width, which would be aspect ratio of 8 or 8.2, right? Another fun fact is that it costed around $1.5 billion to make. A fab cost around $7 billion. So one fab is, people, when you talk about these numbers, right, especially, they don't make any sense. Especially if it's above $1 billion, it's $1 billion or $2 billion, doesn't make any difference. But to keep that in mind, one fab is roughly equivalent to making 4 or more of these towers, right? So keep that number in mind. The tallest tower aspect ratio of 8.2, and the deepest trench aspect ratio of 37. This was featured in Mission Impossible. I don't know how many did people see Mission Impossible? Okay. So increasingly, if you open up a chip, you see things like this. So this is the DRAM chip that you guys did a homework on, the stack capacitor DRAM. So it has these capacitors sticking up, and it looks very much like a skyscraper on a nanoscale. And if you look at the aspect ratio of this, so the height of these capacitors, they're around 2 micron high or 2000 nanometer high. The width is 30 nanometer, and this is essentially determined by Moore's law. So Moore's law wants you to pack more and more of these in a short area. The current technology, it's around 30 nanometer, the diameter of these stack capacitor. So aspect ratio would be 2000 by 30. That is the aspect ratio of 67. So this is the aspect ratio, 6 times higher than the Burj Khalifa Tower. This is the aspect ratio which is twice of that of the Mariana Trench. So this is, it's a very challenging task to make these, to prevent them from falling, and then, to deposit things in between of these. So I'll come to that next, but let's look at some of these high aspect ratio structures. So why do we need this to be that tall? So that requires, some understanding of how the DRAM works. So a DRAM essentially is this capacitor which you saw hanging up in the sky, which is storing this charge. And then you turn this, you select this transistor using that select transistor, and it comes up and charges your bit line. And you detect the increase in voltage in this bit line using a sense amplifier. So for that sense amplifier to detect this voltage, it has to be at least, a few times kT, right? So it has to be at least 6 kT. So it has to be 150 millivolts. And the bit line is essentially you're trying to put more and more transistors or more DRAM cells in series. So the bit line capacitance has been going up. Currently, it's around 100 femtofarads, and the voltage you get on your bit line is essentially just these two capacitors connected in series. So the voltage you get on that node is essentially just series division between these two capacitors. So this thing is going up. So this thing has to also go up. So to keep that, to match it up. So the capacitance that you need on your that tall capacitor is at least 15 femtofarad of capacitance. And that might sound like a very small number, but you have to achieve that in a diameter of 30 nanometer. So to do that, one way to do that is it's a capacitor, so you can increase its K value, and people did do that. And DRAM has been using high K for since 90 or even 130 nanometer technology. So remember, logic or CMOS started using high K at 45 nanometer node, but DRAM has been doing that way back, and they were using aluminum oxide. Now they use hafnium oxide, and they want to go to even higher K material. But there's only little that you can buy by going to higher K. So the way people have been increasing the capacitance is making it using both surfaces and by making it taller. So it's necessary to make this structure taller, and that is one of the main process challenges in DRAM. We looked at, we tore down the iPhone in the first class, and we looked at, it has that yellow colored flash memory chip. Last week we also talked about how these flash memory cells look, and here's a picture of these flash memory cells along a particular word line. So you have these multiple of these cells connected along a word line, and each of these trenches is defining my bit line, which is going perpendicular to this plane. And again, I see these skyscrapers, right? So I see these STI trenches, and I see these skyscrapers of silicon pillars. And again, Moore's law requires me that I pack as many of them as close to possible. And as we discussed in last class, the vertical scaling in flash memory is dead because your voltage does not scale. Your voltage does not scale because your oxide, the tunnel oxide, does not scale. So you essentially are still working at voltages of 20 volts. And if you apply 20 volt between two adjacent cells, you need a very deep trench to separate or isolate these two cells. So if you look at the height here, it's 217 nanometer. The distance between two cells is currently around 20 to between 20. Some vendors are around 30. So aspect ratio of, again, an aspect ratio of 10, much taller, a higher aspect ratio than the Burj Khalifa tower, right? So another place you see high aspect ratio. So another place where you see again these skyscrapers it's a new area for these skyscrapers is in logic. So as logic technology is moving to FinFET, again you need these skyscrapers of silicon fins, and you only make your device in the very top part of the skyscraper, but you need this deep silicon below to isolate your device. And especially for your system on chip where you require higher voltages, this has to be tall enough to give you that isolation. And we also talked about how FinFET scales. So to scale your fin, as you scale your gate length, it only scales if you scale your fin width as well. So essentially these fin widths are becoming thinner and thinner, and so this aspect ratio is going up. Currently it's around 5 to 6, but it's expected to go to 10 in a few technology nodes. So again, we see this problem of, or this challenge of high aspect ratio. So this is something we'll talk about next week, but since we are on the topic of talking about deep trenches, another place, in fact, the deepest trench you see on your wafer currently is when you make these things called through silicon vias. So next week we'll talk about how do we stack these different chips, one being a DRAM, one being a logic processor, another being maybe an analog chip. And when you need to stack them on top of each other, which is required because you want to pack them into your iPhone, which doesn't really have any space for that many chips, so you have to stack them on top of each other. So you dig these holes inside your silicon which allow for these electrical signals to pass through, and they're filled up with metal. It's called a through silicon via because it passes through that entire silicon. So the aspect ratio of these is essentially they have to be as deep as your silicon wafer. So they have to be at least, your silicon wafer at least is 100 micron thick for keeping it mechanically stable. And then you want them to be as small as possible because you want to minimize your layout penalty. If you essentially have these via very large, they'll consume a lot of area on your chip. So you want them to be as thin as possible. And so that essentially results in a very high aspect ratio again. And these aspect ratios here range anywhere between 20 to 100. So aspect ratio of 100 is approximately 3 times of that of your Mariana Trench. So this is 3 times deeper a trench than your Mariana Trench. Right, so how do we make these high aspect ratio structure? One is to how to etch them, right? So we want this etch to be as vertical as possible. So if you have a wet etch that goes as much as it goes vertically, it is the same amount as goes in the horizontal direction. So what you need is a very high anisotropy etch with very good selectivity. You want these sidewalls to be as vertical as possible, and you don't want to damage these sidewalls either. And it's mostly done with this process flow where essentially you etch the thing below. At the same time, you sputter off your etch residue, and it deposits on the sidewall, and it acts like a inhibitor or a protecting layer on the side. So most of these are plasma processes which essentially deposit inhibitor on the side at the same time as you're etching. So what you get is a staircase profile like this. Few things which happen when you're etching structures with this much of a aspect ratio, especially if you're etching a dielectric film, there will be charges building up here, and they cause a closure of this, or they cause this etch profile to become more like a V shape. Also, the other problem is that you get limited flux when you go to higher depth. So this is shown over here. So if you're etching a structure and you're etching, or you're at the very top, you get the flux from your plasma from a very high angle. If you have etched quite a deep, you get the flux from a very limited angle. So this is a major problem when you are etching structures with high aspect ratio, and it causes this phenomenon called as aspect ratio dependent etch. So if you have multiple of these structures with different width, and you are etching them, the structure which is the widest will etch the deepest, and the structure which is the narrowest will etch the smallest. And you can clearly see this, this aspect ratio dependent etch over here. You can also see it over here. So this becomes a big layout problem. So we talked about you can only allow print straight lines, but it seems like you can now only also etch straight lines with a constant width. So some of the things which are new with these high aspect ratio etches is that increasingly people are borrowing tricks from MEMS technology. So you look around and ask who has been etching aspect ratios of hundreds to 1. So it seems like the MEMS people have been doing it for a while, and they use this process called Bosch process, and it's developed by this company Bosch. It's a MEMS company, has a large office in Palo Alto, and what it does is essentially it's a cyclic process between two etch and passivation steps. So what happens is that you have this passivation layer which comes from your etch residue. Then you do a RIE step, so it's a very vertical step, you remove it. And then you etch it slightly deeper, so it causes this barrel. And then you enable that plasma again, so you passivate it again. So it's a cyclic process which is used to etch this high aspect ratio structure. And especially to etch those TSV films that I just showed, you use this kind of process. So you can see this through silicon via, which has a width of 2 micron. And you can see these multiple grooves, each grooves being formed with one of the cyclic etch steps. So this is something showing having 20 etch steps, and it looks very much like an outer surface of a screw. You have, with each of these etch steps, you form this screw kind of a structure, but it's a technology borrowed from MEMS, which is currently used to make this TSV. So not only one theme I want to bring up is that these NAND guys, DRAM guys, and logic guys, they keep on borrowing ideas from each other, and they also keep on borrowing ideas from other fields. So it's an interesting thing which has happened in the last few years. So the point, to coming back to your question, so even though I've etched these structures, how do I maintain their integrity? And it's very hard to do. So this stacked capacitor over here, it has an aspect ratio of 67, and inevitably, whatever any wet processing I do, if I fill it up with a liquid, it will collapse with each other because there will be these forces which would be causing bending, and they will collapse. So there's multiple things people do. There's something called a critical point dry. So you essentially go directly from a liquid phase to just evaporating the liquid. But this bending or these high aspect ratio structure collapsing is the major yield limiter for DRAM today. Same thing happens in these flash memory cell as well. So for your NAND flash, again, you have these multiple of these STI structures standing, and the major yield limiter there again is the collapse between these structures. And this is something I discussed when we talked about FinFET, but it's worth mentioning again that these forces which are causing these lines to bend, they depend essentially on your how tall your structure is. So it's a fourth power of how tall it is. It's inversely dependent on the third power on how wide the structure is. And as we saw, most of these structures are becoming taller and they're becoming thinner. So this problem just multiplies up, and you get a lot of collapse of these structures. Yes?
What are the tall structures in NAND?
The tall structure in the NAND is your STI etch. So this is your word line and this is your bit line, right? So each bit line is separated from another using this STI etch. So this STI etch, so look at this picture. These things over here are essentially these STI etch collapsing into each other. And this is showing more of these STI etch when they're patterned. So they were patterned using, so this is a side view and this is a top view. So you can see on the top view they have collapsed.